There are many shortcuts to high accuracy in medical AI. And in this case, taking a shortcut means compromising human welfare. That's why it's vital that we understand these shortcuts and learn how to detect them before they cause real harm. High accuracy can be deeply misleading. Models that appear to perform brilliantly during training and even testing can fail catastrophically in real-world clinical practice due to such shortcut learning. Let's examine how certain features in our training data can act as shortcuts that undermine the clinical utility of our model. When a feature in our dataset essentially gives away the diagnosis, the model learns a circular relationship that provides no real predictive value. The model becomes dependent on information that simply won't be available when you actually need to make predictions in a clinical setting. The consequence is catastrophic failure at the point of care, exactly when accurate predictions matter most for patient outcomes. Understanding the different forms of data leakage is therefore vital for identifying and preventing these pitfalls in your own work. Target leakage occurs when your features are consequences of the diagnosis rather than true predictors. For example, including a diabetes medication column when predicting diabetes. Temporal leakage involves using information that wouldn't realistically be available at the moment you need to make a clinical prediction. Proxy leakage is more subtle. It involves variables that indirectly encode your target, allowing the model to take a shortcut without directly seeing the answer. Let's consider another example. If you include weight and height in an obesity prediction model, the algorithm will simply learn to calculate BMI and achieve near perfect, but clinically useless accuracy. The real value lies in predicting risk from modifiable lifestyle factors that can inform interventions. When you're reading published research on medical AI, keep in mind that the peer review process itself has significant limitations. Many journal reviewers come from clinical backgrounds and may not recognize algorithm-specific pitfalls like improper data splits or leaky features. Conversely, reviewers with strong algorithmic expertise may not understand clinical workflows well enough to identify when features wouldn't be available in practice. The result is inconsistent evaluation standards and a lack of methodological rigor across the medical AI literature. The field is experiencing what we might call accuracy theater, impressive numbers that mask fundamental problems with clinical applicability. The current incentive structure rewards researchers for claiming high accuracy, regardless of how those numbers were achieved. Studies frequently emphasize quantitative metrics while neglecting to examine whether results would hold up in real-world clinical implementation. This creates a dangerous disconnect where papers claim impressive results, but the models they describe would fail when deployed in actual patient care. Let's look at the evaluation metrics that should be mandatory for any medical AI study claiming clinical relevance. Learning curves plotting accuracy across training can reveal overfitting, underfitting, or suspiciously rapid convergence that suggests the model is exploiting a shortcut. Precision recall curves are vital for imbalanced medical datasets, as they expose the model's true performance on rare but critical classes that other metrics can mask. Confusion matrices should report actual counts, not just percentages. Building trustworthy medical AI requires a collaborative path forward involving education, teamwork, and shared accountability. We must train medical students to understand machine learning methodologies and critically evaluate AI tools so they can ask the right questions before adopting these technologies. Developers and clinicians need to work side by side, each bringing expertise the other lacks to identify potential shortcuts and ensure clinical relevance. We need checks and balances where developers and clinicians hold each other accountable, prioritizing patient outcomes over chasing accuracy numbers for publication. Here are 5 essential questions that anyone adopting or evaluating a medical AI system should be prepared to ask. First, was the data split at the patient level, ensuring that no patient's data appears in both the training and validation or test sets? Second, were leaky features, meaning those unavailable at prediction time in actual clinical practice, identified and removed from the training? Third, what do the learning curves and precision recall curves reveal about the model's training dynamics and robustness? Fourth, How was class imbalance so common in healthcare tasks addressed, particularly for rare conditions where most patients fall into the negative class? Fifth, was external validation conducted to ensure the model generalizes effectively across diverse institutions, time periods, and patient populations, rather than relying solely on data from a nearby sister institution? For those who want to explore these concepts in comprehensive detail, I've written a 2-book series, Diagnosing AI and AI-assisted medical diagnostics, which cover everything from foundational principles to practical implementation guidelines. My name is Dr. Toma. I'm an associate professor of clinical sciences at the College of Osteopathic Medicine, New York Institute of Technology. Thank you for your attention, and I look forward to your questions.